we got a whole lot of information here. We're not going to worry about that information because I've given you maybe all you need or maybe extra. But let's try to work through what's going on here. What I have is some water. And so let me give myself a picture of a beaker, maybe of water. And how much water do I have? I have a liter. And this water is at 25 degrees Celsius. And let's see what else. I'm going to heat it. I'm going to heat it with some methane. Now that's the natural gas. That is what a Bunsen burner, okay? So here's my Bunsen burner and I got a little flame, okay? And half of the energy from here is going to go into here, okay? The rest of the energy, the other half of the energy is going to go to the surroundings, okay? Half the energy is going to go into there, and I want to know how much energy or how much methane has got to burn to convert this all the way from a liquid to a gas, which would be steam, at 100 degrees Celsius. So I'm just going to boil it away. So let's look at the information that's happening here, and then let's translate it to what's happening here. I know that to get the heat that has to go into the water, that there's a couple legs of my journey that I'm going to travel. Let me draw a heating curve. Okay, there's a heating curve. Let's see where we're starting. This is a solid, this is the liquid, this is the gas. This is melting, this is boiling. Now we're starting at a liquid at 25 degrees Celsius. Well, right here is 0 degrees Celsius, and where it boils is 100 degrees Celsius. So we're starting down here somewhere, and I put a little X here where we're starting. And we're going to turn it to steam at 100 degrees Celsius. So we're going to finish right here. Those two legs of the journey. So let's see here. Let's change the pen color and plan this journey. First of all, we're going to travel this leg of the journey. Okay? And that is heating it up. And then we're going to travel this leg of the journey. So let's do those two calculations. Number one. Number one is a change in temperature. So Q for this first step would be the mass of the water, which there's 1 liter. Well, 1 liter, we can't put the mass in there, is 1 liter. So let's come over here and figure out the mass. 1 liter is 1,000 milliliters. And quite often I will just say, well, that's got to be 1,000 grams because the density of water is 1. But they in this problem gave you a little bit more information, and they told me that at 25 degrees Celsius, it's not exactly 1, it's 0.99704. So the mass that I would use in here would be 997 grams. Now they say grams per cubic centimeter. Remember, a cubic centimeter is the same thing as a milliliter. So now I know the mass. 997 grams of water. Now this is water, so we need the specific heat capacity of water in the liquid state. So that's 4.184 joules per gram degree Celsius. And then we need a change in temperature. So it would be final temperature, which it's ending here at 100 degrees Celsius, minus the initial temperature, which is 25 degrees Celsius. This is going to give me 313 joules, or 313 kilojoules. Second leg of the journey. Second leg of the journey involves boiling. The energy associated with boiling is heat of vaporization. So we're going to have to use this information, and that is the kilojoules for every mole of water that's converted. Well, I don't know how many moles of water I have that's converted, so let me figure that out. I had 997 grams of water. So to get moles of water, we would need the molar mass of water, which is 18.0152. And that gives me 55.34 moles. So now for the second leg of the journey, I can say that I have 40 0.79 kilojoules per mole, because that's the heat of vaporization, times 55.34 moles. And this is going to give me a value of 2,257 kilojoules to do step 2. So if we add step 1 and we add step 2 together, we would get a value of 2,570 kilojoules of heat. That is how much heat has to go into the water to convert it. So where is that heat coming from? That heat is coming from the combustion of the methane. Now, if I look up here to heat combustion, now I do see a typo in my chart. Combustion is always exothermic, so this should be a negative number. This is how much heat gets generated every time 1 mole reacts. Well, let's figure out how much heat we need. We need 2,507 kilojoules, but we know that only half of it goes into that. So if we double that number, 2 times 2570, and we change the sign because we have to give it off by the methane in order for it to be absorbed by the water. This is going to give me the amount of heat needing to be generated by the methane to be 5,000, a negative 5147 kilojoules. So that is the heat released by the methane. Okay. Well, how much energy is it going to take? How much methane is it going to take to do that? Well, let's draw a couple lines here so we don't get lost in our work. I have to get this much heat out of the methane. I know that every time I react 1 mole of methane, I will generate 890.4 kilojoules. So that would give me the moles of methane, but it doesn't ask up here the moles of methane. It wants to know the volume of methane. Methane's a gas, so we can use PV equals nRT. Let's go ahead and get a value for the moles. This would be 5.77 moles of CH4. So now how are we going to get the volume? Well, it's a gas. Volume equals nRT over P. N is this 5.77 moles. R, 0.08206. Measured at, what volume is needed, measured at 25 degrees Celsius and 1 atmosphere. So 25 degrees Celsius is 298 Kelvin. Pressure was 1 atmosphere. So V equals nRT over P, and this is going to give me 141 liters. Okay, so that's how you work that problem. And those are the 3 problem-solving things. Now, it always makes sense when you see somebody else do something. So as we continue through this semester, I just want you to realize that we're working on the problem-solving process. I would not necessarily expect you to sit and put your pencil to paper and be able to figure out this process without having to really scratch your head for a while. Drawing pictures, as I've done, sketching it out, seeing where you can go and what needs to come next. Finding yourself at a dead end and starting over are all natural ways of trying to get to your answer. So don't feel like you've got to start and get to the finish without pondering it, because that's not a problem.